Hi, and welcome to video 2 of 3 on Chapter 13. Now, as we discussed last video, um, Chapter 13 deals with gravity, and we had left off with uh, Newton's law of universal gravitation, which, as I said, is a little different from the one that you see in your book. If you think of two objects, we'll say object 1 and object 2 like this. They have masses m1 and m2 and are separated from center to center of mass by a distance of r, then the attraction that they're going to feel is given to us by Newton's universal law of gravitation, which looks like this. Now, so to be clear, this might be the force that object 2 experiences due to object 1, but as per Newton's third law, it'll also be the force that 1 experiences due to 2. Now, just for reference, G is the gravitational constant, and it has a value of 6.67430 times 10 to the minus 11th Newton meters squared per kilogram squared. Now, so in this video, I want to talk a little bit about this equation and show you how it's used, and talk about some of the consequences of gravity being what's called an inverse square force. Now, inverse square means that if you look at this force, it goes like 1 over the distance squared. So, for example, if I were to look at how strong gravity was here at the Earth due to the sun, we'll say, and we'll say the answer A. If I was to double the distance the Earth is away from the sun, I double R. So we'll say I'm 1 AU away, I take it out to 2 AU. So now it would be 2 squared on the bottom. And if you factor this in, you do the math, it ends up being a quarter of this. You take it three times the distance away, it's 1/3 squared on the bottom because it's squared. So it would be, that over 9. So inverse square means that as you get further and further and further away, the force changes and decreases like 1 over r squared. Okay, now gravity is an example of what's called a fundamental force. And by a fundamental force, I mean that the force is generated based upon some innate property of nature. And in this particular case, that innate property is mass. So, with Newton's version of gravity, things that have mass can affect other things that have mass. And as a consequence, what happens is there's a force that's produced between them that's an attractive force, which is the purpose of the minus sign right here. Okay? Now, that said, let's just do some simple examples to get sort of a feel for how this force works. And here's one right here. What is the force felt by the Earth due to the sun, and what acceleration does it feel, specifically in its orbit? So if we're to sort of draw a picture here, here we'll say is the orbit of, the Earth around the sun. And maybe here is the sun in the center of the orbit. And the distance from the sun to, say, the Earth right here is given to us by r. Here's the Earth. It's got its own mass, which I'll call m sub e. The sun has got a mass, m sub s. And you can look these things up. They're actually very well documented. For example, this distance r, remember, is an astronomical unit. But in terms of the metric system and the MKS system is 1.496 times 10 to the 11th meters. Now, the mass of the Earth, again, is something that's very well documented. It's 5.972 times 10 to the 24th kilograms. And the mass of the Sun is 1.988 times 10 to the 30th kilograms. Now, we want to find two things. We want to find basically the force of the sun on the Earth, okay? And we also want to find the acceleration that the Earth experiences in its orbit. Now, this is a centripetal acceleration. Remember, this particular force is what we call a central force or a radial force. It acts through the center of mass of things, okay, towards the center of the circle, if you want to think of it like that. Now, here's a pretty simple calculation. What I'm going to do to sort of fit, the units of what we're doing here, draw my coordinate system. And this right here would be in the r hat direction. It's along r, okay? So my force here, due to gravity of the sun on the Earth, would equal to minus g times the mass of the Earth times the mass of the sun divided by the distance squared along the r hat direction. Now these are positive right here. This is positive, even if it was negative, which doesn't make sense. If you squared it, it'd be positive. So what we have is the inwards acceleration. It's it's in the minus r direction, or minus r hat direction. So let's just plug our stuff in here. Now g, remember, is a constant. It's 6.67430 times 10 to the minus 11th Newton meter squared per kilogram squared. The mass of the Earth is 5.972 times 10 to the 24th kilograms. The mass of the Sun, 1.988 times 10 to the 30th kilograms. And then we're dividing this by the distance squared, which is 1.496 times 10 to the 11th meters. And again, this is in the r hat direction. So if you take and you plug this into your calculator, grab my calculator here, 6.67430 times 10 to the minus 11th times 5.972 times 10 to the 24th times 1.988 times 10 to the 30th. Then divide that by 1.496 times 10 to the 11th, and you got to square that. You get a tremendous amount of force, which it would have to be for it to stay in its orbit because it's a big thing. Whoops, not 5. Let's look at the second digit. It's 3.5406 times 10 to the 22nd newtons, which, well, we have 4 sig figs here, 4 sig figs here, 4 sig figs here. So, 3.541 times 10 to the 22nd newtons. All right, so there's your answer. Now, so that's the force. Now, what about the acceleration? Well, F is equal to ma. This is the force that's acting on, the Earth to cause it to experience acceleration. So if you just think about F being equal to m times a, our acceleration is just going to be this force divided by the mass of the Earth, right? So, 3.5406 times 10 to the 22nd newtons. The mass of the Earth, 5.972 times 10 to the 24th kilograms. And if you do that, so it's divided by 5.972 times 10 to the 24th, you get an acceleration of 5.929 times 10 to the minus third meters per second squared. A very, very, very tiny amount of acceleration. But, I mean, it's a tremendous amount of mass, and the orbit itself is so big that it really doesn't require a whole lot of acceleration to keep it on this path. All right. Now, so let's do another example. What acceleration due to gravity do you feel on the surface of the Earth at sea level, on the equator, or the North and South Pole? Now, so why would you experience a difference between these? Well, the first thing you need to realize is that Earth itself, even though we sort of idealize it as though it's a sphere, isn't. It actually looks more like this. It bulges along the equator. The reason why it bulges along the equator is that it rotates on its axis. So as the Earth rotates like this, with the angular speed of omega, we'll say, mass along this rotational path right here is flung outwards a little bit because of its inertia. So what that does is to cause the Earth to actually bulge along the equator, and the radius of the Earth from the center of the Earth to the equator is different than it would be if it was from the center to the north of the South Pole. How much different? Well, I'm glad you asked. Let's write that as a given. The radius of the Earth at the equator, that would be 6.3781 times 10 to the 6 meters. But at the poles, the North and the South Pole, it's 6.3568 times 10 to the 6 meters. And as you can see, along the equator, it's actually a little bit bigger. All right. And if it's a little bit bigger, that means that if you think of standing here on the equator and your distance relative to the center of the Earth versus standing here on one of the poles, you're actually closer in the poles, which means that you're going to experience, we're going to discover, a slightly different acceleration due to gravity. Okay? So that said, what do we want to find? We want to find what amounts to g, both at the equator and at the poles. All right. So to do that, we're going to need the mass of the Earth, which we already know. I'm going to take this out a couple of extra digits just because I have a couple of extra digits here. 5.97237 times 10 to the 24th kilograms. Okay. So, force we know. If you think of this person, we'll say as having a mass of P, massive person. So the force of the Earth on the person, which would, now let's not forget, that force is acting on the person's mass to cause it to experience acceleration, right? Would be minus g, mass of the Earth, mass of the person, divided by the distance between the center and where the person is squared along the r hat direction. So if you think about just what the acceleration is, the masses here cancel out. And once again, it should make sense to you that the acceleration due to gravity would affect all masses the same way. Now, just for the sake of making things convenient, I'm going to drop the vector notation here because we're just looking at magnitudes. What do you know is going to be through the center? And let's start with the equator first. So the acceleration there, we're going to call g sub b. That's the acceleration due to gravity. And it would be g times the mass of the Earth divided by the radius at the equator squared. So this is the equator. Now, g from before is 6.67430 times 10 to the minus 11th Newton meters squared per coulomb, or kilogram squares rather. The mass of the Earth we have here is 5.97237 times 10 to the 24th kilograms. And at the equator, Our radius is 6.3781 times 10 to the 6 meters, and we're going to have to square that. So what's our acceleration due to gravity here? Well, let's see here. 6.67430 times 10 to the minus 11th times 5.97237 times 10 to the 24th. And then we have to divide that by the radius of the Earth at the equator squared, which would be 6.3781. Oops, 3781. A little bit of a typo there. Times 10 to the 6. We got to square that. And I get here, taken out to, let's see, what do we have? 2, 4, 5, 2, 4, 5, 2, 4, 6, 2, 4. Okay, so 5 significant digits. 9.7987 meters per second squared. Okay, so now let's do the calculation for the acceleration due to gravity at the poles. So it's the same calculation as what we just did. So what I'm going to do is I'm going to snipe this. I'm going to put it over here, and we'll just clean this up a little bit, make it clear as to what it is. Get rid of our radius there. And so this would be at the poles, right? So here, like I said, it's the same calculation, except now we're using this radius right here. That is 6.3568 times 10 to the 6. So if you redo that calculation and just change that, so 3568, you get 9.8645. Whoops, not times. Meters per second squared. So, I mean, it doesn't look like much of a difference, but, if you do a fractional difference there, let's just do that. 0.7987. That's about a 0.67-ish percent difference between this and this. Okay, so there is a difference. So I guess one lesson here is that, and as you can imagine, as you go this way from the equator, this is latitude, by the way. If you go up in latitude, here what happens is you're going to naturally weigh more because of the fact that you're experiencing this acceleration due to gravity that's just a little bit greater. So if you live on the North Pole and you want to lose a pound or two, just fly to the equator and live there, and you'll weigh a little bit less. That's the kind of diet plan I like. So next up, what I'd like to talk about before we get into a discussion about energy is the fact that the Earth does rotate. So if you think of this right here, sort of as the Earth here, and let me once again draw our axes here. Here we go. This rotates like that. Now, if you were to stand here, we'll say, and think about the direction that gravity is pulling you, it would be pulling you straight towards the center like this. However, there is, let's Let's see, is this going to be like that? Let's see if I can move it up over here. However, at where you stand right here, whoops. There we go. We'll try moving that again. Sorry about that. There we go. So what happens is as the Earth rotates, we'll say, this way right here. As the Earth rotates, you experience centripetal effects this way, as well as gravity pulling you this way. Okay. Now, so this is because the Earth is rotating and you have mass, and the mass of your body says, I want to keep going this way, I want to keep going this way, I want to keep going this way. It's the same reason why the Earth bulges at the equator. Okay, now this effect is far, far less than the pull due to gravity, so you don't go flying out into space. Okay. So in reality, if you were to weigh yourself on a scale, we'll say, you actually have two effects here. And so when you weigh yourself on a scale, you're getting what you would say an effective gravity and not the actual true weight that you have. Okay. So this right here would be the radius of your centripetal acceleration right here. This right here. And typically what we do is we call this right here, this is latitude, and we use the Greek letter lambda for the angle for latitude. And this right here would be r, like in our equation for gravity. Okay. So this right here, this radius of our orbit, if you think of this as the radius of the Earth right here, this radius of our motion around as we go is going to be, in terms of latitude, the cosine part. So if I call this rho would equal to r times cosine of lambda. And in truth, were you to take a more complicated mechanics course, you would talk about this in terms of rotating coordinate systems, because here, as you stand on the surface of the Earth and the Earth rotates, you are in a non-inertial coordinate system, which means that you're experiencing effects merely due to the fact that you're being accelerated out around in the circle. Okay, so now I want you to imagine a situation where instead of standing way up here, now we're standing on the equator. So if we're standing on the equator, the radius of the Earth at the equator would also be the same as the radius of the circle that we would be going around due to the Earth's rotation. And because of that, you can actually sort of get a feel for the difference between what the gravitational force would be and what this sort of, we call it the centrifugal force. Now, it's not a real force. We talked about this before. This is an effect due to the fact that you live in a non-inertial frame. Okay. But it does affect you. That's the thing. It's not a force. There's no underlying phenomena in nature that you can point to that says this is what's creating the force because of this. Okay, but it is an effect, like I said. And so, were you to say sum up the forces of someone who's standing here, and we're going to use the old version of gravity, just mg for the time being, to make our life easy here. You would have, if you were to think about that person sort of standing there, let me draw a force diagram on them. So here you are standing on the equator like this, and you got your weight pulling you down like this, right? But then you have that inertial rotation trying to fling you out like this, which isn't a force, to be clear. It's an effect. But we'll call this right here, this sort of effective force, F effective. Okay? And here's your weight, which we're just going to write as m times g. Now, these two in this particular case would add up to cause centripetal force. So here, when you sum up your force here, which would be this effective force plus the weight, this is going to act on your mass to cause acceleration. And in this case right here, this acceleration is going to be inwards because weight is far greater than what this effect is. And, you know, in the R direction, which this would be in the R direction out like that, because it would be this way right here if you think of standing like that. You would have your effective force minus mg is equal to minus mv squared over r. Now, v would be your tangential velocity as you go around in a circle. But we know from our discussion of rotational motion that v here is just equal to r times omega, omega being your angular velocity. And in here, so if you plug that in, that's minus m r omega squared. So what that means is that my effective force here, this effect of centrifugal whatever going on here, is equal to mg minus mr omega squared, or m times g minus, now the r here would be the radius of the Earth at the equator, and this omega we're going to calculate here in a second. Omega itself, you go around the Earth once every 24 hours. Okay, so 2 pi divided by, if you do the math here, 24 times 3,600. So 86,400 seconds. So this would be the angular velocity as you go around. Okay. Now, so what I'm going to do is I'm going to call this first term right here, okay, I'm going to call this term right here from the acceleration standpoint 1. And I'm going to call this one right here 2. And I want to calculate them separately. I mean, we already know what g is. In fact, we could go over here and we could just take a look at what, the acceleration due to gravity at the equator is. It's this number right here. So why don't we just snag that? Now, we also need to know what the radius of the Earth is at the equator, which we have right here. Whoops, wow, that was a trip. I'm thinking no on that one, right? There we go. So let me just snag that again. Here, move it here. So here, part 2, this other equation over here, when you calculate this, it would be 6.3781 times 10 to the 6 meters times 2 pi over 86,400 seconds. And you got to square that. So, let's see here. Times pi. Divide that by... and then we're going to multiply that by 6.378. 1 times 10 to the 6. And I get something like 0.00538 meters per second squared. Now compare this to this right here. This is trivial. This is a tiny, 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 tiny amount of effect. In fact, you can do a ratio if you divide that number right here by this number right here, 0.7987, and then multiply that by 100. This amounts to something like 0.055% approximately, the amount. So, and as you can imagine, um, the strongest effect you would feel this, or strongest space where you would feel this would be here, because it's here where R would be at the greatest. Okay, so if you look at this right here, or this right here, it doesn't matter. Your angular velocity at this point, or at this point, or at this point, or all points along the surface of the Earth here, except obviously in the water, is going to be the same. This doesn't change. But what does change is this: as you go up in latitude, this rho here, this actual radius based upon your point of rotation, that's going to change, and it's going to be at its largest at the equator, and it's going to be zero up here. Okay, so this is the biggest this effect gets to be, and this is trivial. So naturally, we can neglect this, at least when it comes to things that are on the surface of the Earth. Now, however, were you to fire something into the air, okay, then its trajectory would be affected by the rotation of the Earth, and also possibly, other effects as well, centrifugal, uh, potentially, as well as, you know, uh, just the fact that you're now above the ground and your acceleration due to gravity is different. Okay, so just a side note that, you do have these centrifugal effects that occur because we live in a rotating coordinate system. Like I said, for those of you that are going to go on and take something more complicated, you'll learn far more about this in a class called classical mechanics. Now, what I would like to do, though, just to introduce the concept, because this will be incredibly important in university physics too, is to talk about something called fields. Now, when I say a force field, I don't mean like something, from Star Wars, or Star Trek or wherever. When I say a field, what I mean is a mathematical function that um, describes some quantity at all points in space. Okay. Now, in general, this is a vector field, and here's the reason why we're interested in these things. All of the forces, with the exception of gravity that we've talked about, have a visible way in which they convey their connection. So, for example, if you pick something up off the floor, you are exerting the force very visibly through contact. There is an obvious point of contact. If you are using pulleys and cables and stuff, there is a point in which things are in contact. But gravity is what's called an action force. It's an at a distance force. So it's possible, and in fact, that's what it does, is it affects things over great distances with no clear connection, no obvious connection or physical connection. So how does it do it? Where does this connection come through? Where does it come in? Well, that's in what we call the field. The idea is this. So you have some property, we'll say mass, and the act of having mass generates what's called a field. And this field sits out at all points in space. And when you take and you put another mass in its presence, that creates a force. So, for example, the sun has a mass. If you take and you place a planet in the presence of the field created by this mass, there's a force generated, on the planet due to the presence of the field. Now, if you think about that, we can sort of deduce as to what the field is going to look like. So the force we know between these things is minus g mass of, we'll say, sun, mass of planet, divided by the distance between the two along the r hat direction. But this force is generated when you place this mass a distance of r away from the sun. So the field, which we're going to call g vector, is really equal to minus g times the mass of the thing doing the gravitating, the mass of the thing creating the field. Like that. Now, this right here is what's called the gravitational field. Okay. Now, so it looks like something. In fact, if you look here, if you think of this as the Earth having a mass of m sub e, the field goes in towards the center. You'll see these little arrows here. This is the direction of the vector field. As you can see here in our equation, it's in the minus r hat direction. It only depends upon r. It doesn't depend upon angles or anything like that. Okay? It only depends upon r. So this is a radial field that goes in towards the center of something that has mass. Okay? Now, were you to place an object here that has a mass, it's going to experience a force that is in the same direction as the field line. That's what these are called. These are called field lines. Now, I'd like to point something out here. If you look at the form of this equation, the gravitational field and the force itself is only zero at one place in the universe, and that is when r goes to infinity. So as a consequence, there is no place in the universe that you can go to in which you will experience no gravity. Gravity's everywhere. Okay, even when you go up into orbit and they say you're in 0G, that's nonsense. You're in a situation called microgravity. That is, the acceleration that you feel due to gravity is down around the third decimal place. Like this over here. Like that. Okay. But it's still there. It's still there. There's no place in the universe that you can go to get away from the pull of gravity. Now we're going to be talking more about this in the third video, specifically when we just talk about Einstein's version of gravity a little bit. We're not going to go into any incredible mathematical detail because we don't have the tools for it. So another thing I want to talk about is actually something that we already know. And that's the fact that gravity itself is a conservative force. If it's a conservative force, that means that we can define a potential energy and use that through conservation of energy to do problems. So I want you to imagine a situation to where we have a mass, we'll say, sitting at the center of the Earth. And what we're going to do is we're going to punt this thing really hard and cause it to race outwards this way, past point R2. Now, here, our force is acting this way, trying to pull the mass back into the Earth. But this right here is the direction of our displacement, dr. So dr is this way, and our force is this way. Okay? Now, so in this case, when you do the dot product between the force due to gravity and dr, you're going to get a negative sign. So our work, which is the same thing as our change in potential energy, okay, or a negative change in potential energy rather, is going to come from integrating dw. And in this case, dw is going to equal to f sub g dot dr, or minus g mass of the Earth, mass of the object, which I'll just call m as it leaves, over the distance squared, dr. Now when I integrate this, let me just pull the stuff out here that's constant. When I integrate this, I'm starting from the center of the Earth, which I'll call R1, and going to R2. Now, technically, you would call R1 0, but look, the issue that you have here is when you integrate this, you end up with a 1 over R, and you put a 0 in there, and you have something that's undefined. So what we're going to do is we're going to use the convention that we're familiar with, and that's at the center, where you can't go any further. Our potential energy is 0. Now, it turns out that actually works because if you have something sitting here, the force due to gravity actually balances itself out, and you end up with it staying there due to the fact that the net force is equal to zero. So that's not an unreasonable assumption to make. So here, again, our potential energy at location 1 is 0. What we're looking for is this, our potential energy at location 2. Okay? So here, if I integrate this, I end up with a minus 1 over r. That hits this minus and makes it positive. And we have to evaluate this from r1 to r2. Now, like I said, at r1, this thing is defined to be 0. At r2, though, it's not. So let's just go ahead and plug this stuff in. Well, actually, I don't want to put the over there yet because it is 1 over r2 minus 1 over r1. This is defined to be 0. And this, again, is equal to the change in potential energy. The change in potential energy is final potential energy minus initial potential energy. Our initial point is location 1. That's 0. So there's a minus sign here, which will move to the other side. And our potential energy as a function of r here is minus g mass of the Earth, mass of the thing moving away over r. Or, if you write it sort of in general, it's going to be G m1 m2 over r12, r12 being the distance between the two. So this is the sort of full-blown potential energy due to the gravitational force right here, and it's negative again. And one thing I'd like to point out is that we say that things are gravitationally bound to stuff when the total energy, which would be the kinetic energy plus the potential energy, is less than or equal to 0. Okay? In fact, it's technically less because equal to is what we call escape velocity. And we're actually going to explore that next. What is the escape velocity of a rocket launching off of the equator of the Earth? So, here's the Earth. Here's the equator, we'll say. Here's the center right here. The rocket starts here at the surface of the Earth. So your initial energy in this rocket is going to be whatever velocity it launches off with. We're going to assume that it's just basically kicked with whatever velocity is required to escape, plus the potential energy that it has there. And the potential energy it has is going to be due to how far above the center of the Earth it is. Now, way, way, way far out over here, where our potential energy is 0, that would be out at infinity. So far away, that's you can't reach it basically. Out over here, we want our rocket to slow down and stop at exactly that point. That's exactly the required energy that is needed to make this thing escape fully the gravitational attraction of the Earth. So out over here, what we want is a condition in which our potential energy and our kinetic energy, it's come to rest at this exact point, and there's no potential to move beyond it due to this potential energy here. This is equal to 0. Okay? So our initial kinetic energy here would equal to 1/2 mass of our rocket times v squared, our initial velocity that is. And our potential energy here would be minus g mass of the Earth, mass of the rocket, divided by the distance from the center to where the rocket is, which would be the equatorial radius. Okay? So, again, energy is conserved. Our initial energy is equal to our final energy, but our final energy is equal to 0. So what that means is that 1/2 mv0 squared minus g mass of the Earth, mass of the rocket divided by r sub e, that's equal to 0. and the mass of the rocket doesn't matter, which should make sense. Again, gravity causes all things to experience the same acceleration. So if I solve for v here, I get 2g mass of the Earth over radius of the Earth at the equator, square root of. And I can plug this stuff in from previous information that we were given. If you remember, G was, let me get my sheet here with all this data on it. G is 6.67430 times 10 to minus 11th Newton meters squared per kilogram squared. M sub E is the mass of the Earth. 5.972 times 10 to the 24th kilograms. And R sub B is the equatorial radius of the Earth, which is 6.3781 times 10 to the 6 meters. So if you take and you plug this into a calculator, you get, let's see here, 2 times 6.6743 times 10 to the minus 11th times 5.972 times 10 to the 24th divided by 6.3781 times 10 to the 6, square root all that, I get 11,179 meters per second. Or in general, we write this as 11 kilometers per second. So if you want to get, for example, a probe away from the Earth around the moon and, out to another planet, this is roughly how fast this thing needs to be traveling. If it were launched initially, from rest and just with a huge kick to give it 11 kilometers per second. So this is the escape velocity is what we call that. And that's typically written as V sub E or V sub escape. All right. Now, we're actually going to come back and visit this later on because when we talk a little bit about at the end of this chapter about general relativity, I'm going to talk a little bit about black holes. And one of the things that defines a black hole as a black hole is the fact that its escape velocity is the speed of light or greater, which is 3 times 10 to the 8th meters per second. So that means light can't get away from it, which means that it appears to be black. Now, let's work another example. So the sword of Damocles is the name given to a kinetic energy weapon that sits in orbit above a battlefield, waiting to fall upon a given target. Now, if geosynchronous orbit is 35,786 kilometers above the Earth's equator, how much kinetic energy upon impact would an H-beam of iron? Now, an H-beam is one of those big iron girders that you see used in constructing buildings. This one has the H part is 1 meter, the center part is 1 meter, and it's 10 meters long. That thing has a mass of about 22,000 kilograms. And I want to know what kinetic energy it would have when it hit the ground if it were launched straight down with an initial velocity of 50 meters per second to sort of get it going. And I want to know how many kilotons this would be. A kiloton is a measurement, and we've discussed this before a little bit. A kiloton is a measurement of energy that's typically related to things like explosions and stuff. So what you have here is the following. So we'll say that this right here is the surface of the Earth. This right here is where your equatorial radius of orbit would be, and down here is the center. So So at the surface of the Earth here, if you think about the energy that you have present, okay, you're going to have the kinetic energy of that thing when it hits the ground, plus any remaining potential energy that it may have, to reach the center. Okay. Now up here upon release, so here this we call them sometimes flying crowbars. This crowbar is sitting up here waiting to hit something like a tank or whatever, who knows. Um, and up here, it's sitting with an initial energy of its kinetic energy plus the potential energy that it has up here in orbit. Okay. Now, so let's think about what we've been given here. We're given that the distance, I'm going to call this r sub g for geosynchronous. The distance above the ground for this is 3.5786 times 10 to the 3, 4, 5, 6, 7, 10 to the 7th meters. But we also know that the Earth has a radius, since this sits above the equator, of 6.3781 times 10 to the 6 meters. We know the mass of the Earth, 5.972 times 10 to the 24th kilograms. We know the mass of the girder, which I'll just call M, which is 22,148 kilograms. We know its initial velocity is 50 meters per second as its speed, and it's going to be down, but we don't have to worry about that. We already know that. Now, what are we trying to find? I want to find the kinetic energy upon impact. Okay. Now, so let's talk about what our energies are going to look like. So our kinetic energy is going to look like 1/2 the mass of that crowbar, that girder, which is just m, times v naught squared. Now, our potential energy, though, is negative, remember? And it's going to look like g, the mass of the Earth, the mass of the girder, divided by the radius of the Earth plus how high above the ground it is. That's the total distance from the center that it sits. Now, upon impact, you have your kinetic energy, which is what we're looking for, plus, or rather minus, g, mass of the Earth, mass of the crowbar, divided by r sub e now, because you've reached the ground level. Now, all we're looking for here is k, and these things are equal, because of conservation of energy. So I have 1/2 m v naught squared minus g, mass of the Earth, mass of the crowbar, divided by r sub e plus r sub g, is equal to k minus g, mass of the Earth, mass of the crowbar, divided by r sub e. And all I'm doing is solving for k, like I said. So k here is going to equal to, when you solve for it, 1/2 m v naught squared minus g, mass of the Earth, mass of the crowbar, times 1 over r sub e plus r sub g plus, actually, if it moves over there, it's plus. If you pull into the negative, it's minus. 1 over r sub e. So that's a pretty big thing. Let's do this calculation here. 1/2 m, 22,148 kilograms. V, 50 meters per second squared, minus G is 6.6743 times 10 to the minus 11th Newton meter squared per kilogram squared. Mass of the Earth, 5.972 times 10 to the 24th kilograms. Mass of our crowbar, 22,148 kilograms. Now, 1 over R sub E plus R sub G. That's R sub B plus R sub G minus 1 over R sub E. Okay. So it's a pretty big calculation. So what I'm going to do is I'll do this in parts. So I'll do the first part, which is just the kinetic energy. And, whoops, that's a mistake. That should be times. So for the first part, if you do this, you get 2.7685 times 10 to the, this 3, 6, 7th, 10 to the 7th joules. So this is the first part right here. Minus, now let me do this, the long one right here. Let's see, 6.6743 times 10 to the minus 11th times 5.972 times 10 to the 24th times 22,148 times, now here comes the big stuff, 1 divided by 6.3781 times 10 to the 6 plus 3.5786 times 10 to the 7th. That takes care of that first term, and now I need to subtract away 1 divided by 6.3781 times 10 to the 6. And if I do that, I get this part right here is negative 1.1747 times 10 to the 12th joules. So when you combine those, they add. So 2.7685 times 10 to the 7th. All right, so it's not going to really affect things except out at, say, the 1, 2, 3, 4, 5th decimal place, maybe. So, and we don't even have that there. So this ends up being roughly around 1.1747 times 10 to the 12th joules. Now, if you look here, 1 kiloton is 4.184 times 10 to the 12th joules. So if you were to, convert this to kilotons, you end up with this being something like 0.28 08, we'll say, kilotons. Now, so why kilotons? Well, all right. Um, so, during World War II, the United States made the unfortunate decision to drop not a nuclear weapon, but an atomic bomb on Japan, two of them. One of them was called Fat Man. Fat Man had a blast yield of about 21 kilotons. Another one was called Little Boy. And Little Boy had a blast yield of about 15 kilotons. It's called kilotons because that's in tons of, or thousands of tons of TNT. Um, and in fact, at least in the United States, um, the the largest, most powerful conventional weapon that is, it doesn't use some sort of nuclear source to to detonate or to cause the damage. Um, is something called a MOAB. Um, they're jokingly called the mother of all bombs. It's actually a massive ordnance air blast. Uh, these are the worst ones we have, and they clock in somewhere around 11 tons. So keep that in mind. This is the most explosive, the most powerful conventional weapon that we have. You drop a girder from orbit, and when it hits the ground, it hits with a yield that's 280.8 tons as opposed to 11. So if you do the math, this is about 25 times the explosive power. Now, of course, this is not good. Who wants to drop bombs on people? But this is also one of the justifications that we made to jump into the space race. Way back in the 50s, and that was because Russia put a satellite up in orbit. And if Russia was able to put a satellite up in orbit, imagine what would happen if they were able to get a foothold on the moon and then throw just big boulders at targets on the ground. These things, when they hit us, would hit literally like nuclear weapons, but with no fallout. So, from a military standpoint, space dominance is where it's at. That's the reason why we're getting back into it now that China has decided to spend a lot of time up in orbit. Now we're looking at it as well, just because we have to, maintain quote unquote military superiority. Okay, so this is it for this video right now. Next video, we're going to talk a little bit more about this. We're also going to talk about the tides, why they occur, and then we'll get into a little bit about Einstein's version of gravity. And I'll see you then.